I'd like to introduce us to our final speaker for this session, and that's Claudio Macconi. He's from Turin in Italy. He's a member of the IAU, PhD in mathematics from King's College London. He's published 5 mathematical books on telecommunications, the Carhoonen-Loewy transform, and relativity, the sun as a gravitational lens, deep space flight communications, and mathematical SETI. He's published 203 scientific papers and scientific and technical papers. He's technical director of the IAA from 2010 to current. He's the chair of the IAA SETI Permanent Committee from 2012 to 21, and he's the chair of the IAA Moon Farside Protection Permanent Committee to 2021 to present.
It's okay.
That's okay, yeah, okay. I'll leave it to you.
Thank you. Well, good morning, everybody. Sorry about my poor English. Let me just say that I'm very grateful to the organizers of this conference. I think it was really high time to have a conference like this. And so I just mentioned 2 people, of course, Les Johnson, that I've been working with for ages, decades, and the president of the IEA, John Schumacher, who also is leading forward to the progress in this field. Thank you. So, basically, the topic of my presentation is using a phenomenon, physical phenomenon, a bonanza discovery that was made over the last, let me say 50 years. Essentially, the first equations were given by Einstein himself in 1936, but he did not know about spaceflight. So with all due respect to Einstein, he just died before space age began, and we are now doing the rest. We are just using this fantastic discovery that he made as the future, the present and the future. Okay. Also, my paper is written in conjunction with Nicolò Antonietti, who is the gentleman over there. Nicolò, raise your hand, please. Good. Thank you. And it's also helped me a lot to come over here, because yesterday we flew all the way from Italy to this place, and without his help, I would not have been able to be here today. So, thanks very much. And now, very quickly, the presentation outline. First of all, I have to mention what is the focal sphere. So it's a sphere around the sun, and I call it the focal sphere because the minimal focal distance of the sun as a gravitational lens is just that sphere. And this is located at 550 astronomical units. 1 astronomical unit is the distance between the sun and us, the Earth. So it's pretty far out, but let me say not too far out, meaning that it's already in the human capability, even now, technologically speaking, to reach that sphere with some space mission that I just dubbed focal, because it reaches the focal sphere of the sun as a gravitational lens. Second, interstellar radio bridge. This is a new, this is an idea that I've been trying to push forward, because basically there are 2 different ways to exploit this fantastic phenomenon of the sun as a gravitational lens. One way is the one that will be presented today in the afternoon by Dr. Victor Toth, who is, raise your hand, please, Victor. Good. And that is exploiting the sun as a gravitational lens to watch at extrasolar planets, period. The other way is the way that Nicolò and I are using now, that is to exploit the gravitational lens of the sun for interstellar communication, that is radio communication across the huge interstellar distances, okay? So this is, of course, more for the future, not for the present. But anyway, I'm glad to say that NASA in 2020 put out of the pocket $2 million or something like that in order to have a new generation of young people working on this. And Victor and I and Slava Turicev and other people working on this are most happy about that. Okay. So very, very, very quickly, let me take this microphone. Yeah, very, very quickly. The focal sphere of the Sun at 550 AU and focal space missions, not just one, but several, at 550 AU and beyond. As I said, this was founded by NASA, $2 million in 2020, and Slava Turicev and Les Johnson are the two leaders, Slava Turicev at the JPL and Les Johnson at Marshall Space Flight Center. Okay, this was my book. It's an old book. I published that in 2009, and please correct me if I am wrong, but essentially it is this still one of the few or the only technical books that students can read and learn about with all the equation for this physical phenomenon. It is very expensive. I apologize. It's not my fault. It is the publishers. Okay, let's go ahead. So what is this? Look, this is the Sun. The circle is the Sun. Just imagine that on the other side, this way at infinity, there is a source of electromagnetic waves. Could be anything. Could be a quasar, could be a radio galaxy, could be an extraterrestrial civilization, which I've been working about because for 9 years I was the chair of the IAA SETI Permanent Committee. So initially, I started working on this for SETI purposes, that is to find extraterrestrial across interstellar distances. Anyway, the radio waves or whatever electromagnetic waves arrive close to the Sun, and those that graze the surface of the Sun are made by gravity, and we must use Einstein's Relativity, not Newton's theory, are made to focus on the other side. So this is the minimal focal distance that any spacecraft, and in my imagination, spacecraft means a big antenna, 12 meters dish or something like what you want. This is the minimal focal distance that our spacecraft has to reach in order to look back at the Sun and to see a very largely magnified image, or radio image, of course, of what is on the other side. So this is the basic configuration. And this is the key equation from Einstein in general relativity in 1915. So this deflection angle here, alpha, I call it alpha, this deflection is given by 4 times the gravitational constant times the mass of the Sun over c squared times r. R is the distance. Sorry. R is what in particle physics is called the impact parameter, or B, or whatever. That is the distance between the axis and where the waves pass nearby the Sun. Okay? Good. So this is the contribution by Einstein. But I have to say that it was basically the only contribution because, of course, he didn't know about spaceflight. So from that figure that I just showed you, it's a very trivial calculation that I invite all students and lay people to do. You can immediately find the minimal focal distance. And what you finally find is that the minimal focal distance that your spacecraft has to reach is c squared over 4 capital G times, this is the important part, the square of the physical radius of the Sun or whatever body over the mass. This is the important thing. Okay, good. I told you that for the Sun, this distance is basically 550 astronomical unit, which means 3.17 light days, which means 13.8 the Sun to Pluto distance. Good. This applies to any spherical objects, any spherical mass. So this brings you, for instance, the question, okay, what about the solar system? We have plenty of spherical objects. And the answer is we have a full set of spherical sphere for each object, but they are not the same sphere as we imagine intuitively by increasing distance because of this factor that I mentioned, the square physics, or the square of the radius over the mass. And so this shows you the sun is at the center, of course. The orange thing is 550 astronomical units, the minimal distance. Then the 1000 AU, which is the same story, but keeping in mind the coronal effect, because unfortunately there are electrons in the corona, and they have a divergent gravitational effect on the radio waves, okay? So really, if you want to do good work, you must reach, roughly speaking, 1000 astronomical units. And then this is the sphere for Jupiter and for all the other planets. And the red one, the thick red one, is for Earth. Okay, so this is already a sort of set of focal sphere that was unknown before we did all these things. Okay, gain. Now, of course, every star acts like an antenna. And this equation in yellow is the equation. Of course, I cannot prove it here, but this comes from general relativity, not from Newtonian physics, okay? The off-axis, well, there is just a word. There is this Bessel function of order 0, J0 squared, which means in practical terms that you need a strict alignment between the source, the center of the sun, and the position of the spacecraft. So we have to be careful. But frankly speaking, I do not regard that as an obstacle beyond the possibility of solving it. It's just a matter of having a good control system on the spacecraft, and that the system will compensate automatically for keeping in line. The important point is that the total, I mean, this is the equation by Einstein is just the first equation. But then you have to add the gain of the spacecraft, because you don't look at that just without the spacecraft. And the gain of the spacecraft is proportional to the square. So the conclusion, the total gain is the gain of the star times the gain of the antenna. And so in conclusion, this goes with the cube of the frequency, that is the inverse square of the lambda, the wavelengths. Good. Now we come to the real novelty. I mean, what I've been describing so far was already in my book in 2009. And that certainly helped the cause, because NASA actually funded $2 million, whatever. But now is what I regard as the most innovative part. I won't go through all the equations because there is no time and I don't want to bother you with these things. But let me tell you in plain words, what is this? Imagine, please, you have two stars, not just one star, two stars. For instance, in the paper that we are working on, Niccolò Antonietti and I, one star, of course, is the sun. But we consider another star. The nearest star is obviously Proxima, which is a very modest star. It's a poor star. It doesn't work very nicely as a gravitational lens. But just consider that, please, because this is the closest star, and so it will be, I think, the first star that we will ever reach with the spacecraft. Okay? So, if you have two stars, then my suggestion is, okay, let me explain this without mathematics. The suggestion is, first of all, we need to send a spacecraft around the sun so that as long as the real interstellar probe keeps radio link all the way until it reaches Alpha Centauri or Proxima or whatever it is. Sorry. When it gets there, my suggestion is put it, please, on the opposite side of the sun with respect to the star you have reached. For instance, Proxima or Alpha Centauri A, which is a much better star for gravitational lens. And so in the conclusion, at the end of this thing, you will have two stars, more or less both with the mass of the sun, hopefully, and two spacecraft on the opposite side. So the straight line will have 4 points. We must keep the alignment strict. But if you can do that, I cannot go through the whole story, but if you can do that, you get a fantastic decrease in the powers needed for interstellar communication between the two systems, because you have two stars helping you, all right? So this is very good, and it was not known until recently. I'm not going through the calculation, but essentially this is the idea. Okay, you got the physics. Now please work about another idea, the channel capacity. So we are now shifting over to another branch of physics, which is information theory that was already mentioned before in this morning. Now, Claude Shannon, an American engineer and excellent mathematician, published in 1948 the famous information theory, what classical, then it was extended into quantum, but just classical is enough. And he found the capacity of any communication channel across whatever, wherever are the two stations, the transmitting one and the receiving one. And these are the equations. W is the bandwidth, log 2 is log 2, 1 plus signal to noise ratio. And this is the equation. Now, clearly, all practical bandwidths are finite. But if you really want to dream, or at least if you want to extend to set up a sort of upper limit that physics does not allow you to go beyond, then you take the limit of this equation by W approaching infinity, by L'Hospital's rules, and you get this. So, in conclusion, this is the maximum amount of information that the stars around us allow you to use, period. Okay, I am cutting short, but for instance, with the sun working as a gravitational lens, the maximum capacity at infinity for infinite band is 190 gigabit per second, whereas without the sun, it's only 15.3 kilobits per second. So that gives you the idea of the difference between the numbers. And clearly, we must use this fantastic phenomenon for future interstellar missions. Okay, good. Now, here is already what I mentioned. Now, let's go over to the solar neighborhood. Well, astronomers have been doing a good work, and we have a pretty good list of stars nearby the sun with distances, sizes, that is, gravitational lensing. So we know already about that. And what Nicolò and I are working about is to find out of this huge set of stars, which is the best trail for human expansion in the nearby interstellar space in order to keep the link, okay? At the moment, I am not able to tell you what the trail will be. We are working on this, but essentially, this is the final goal of our research. That is, because of this mixture of general relativity and channel capacities and all that, clearly there must be one trajectory in the nearby interstellar space that enables us to keep the radio link as long as we proceed away from the sun. And I assume that this is basic for human interstellar expansion, okay? I'll cut short. Okay, one more point, please. I mentioned that all this has been done by using Einstein's Relativity, which is the best theory of gravity we have. But I have to mention that what I've been using and presenting here is just the classical Schwarzschild. I know that in America people say Schwarzschild, but anyway, I'm using the German pronunciation. Schwarzschild solution to the Einstein Field Equation. And this is the minimum thing that you can do. But here in America, there has been a school led by Roman Kezerashvili at City Tech, where Greg is teaching and has been teaching. And essentially, Roman and his school were able to use other solutions to the Einstein field equation, the Kerr-Newman solution, to be more precise. So it's only a matter of using those things that were discovered already, apply them correctly, and finding out the trail in space. how many nearby stars? We can decide whatever we please. I mean, humanity of the future can decide whatever they please. It's very difficult to establish even a scale of times. Previously, the Fermi paradox has been mentioned. Fermi paradox is just a way of saying why we have no proof that extraterrestrials have been visiting the Earth in the past. I'm saying we have no proof. They might have been here, but we have, the scientists, don't have any proof. So, conclusion of the story, we can decide as many stars we want to visit. But essentially, if you want to do serious work, you have to take into account the amount of time reached for every successive expansion that we make, okay? For instance, the Europeans arrived here in 1492, and it took 500 years before the United States became the first country in the world for progress of science. So hopefully, or whatever, similar amount of time will be necessary for developing a new civilization wherever we reach. So if you want to consider the times in the future by which we can achieve that, it's a complicated matter. We will try to do something. Personally, I favor the so-called corral model of human expansion in the nearby set of stars. But of course, you can choose other models. The point, unfortunately, is that the number of radio bridges is huge because you need 2 stars for every radio bridge, okay? So if you consider n stars, the number of bridges that you have to compute in order to understand what the hell you are doing, it is n times n minus 1, which is a huge amount of work. Let me tell you something. Antonietti and I, last year in 2022, we presented a paper about this at the International Astronautical Congress. Now, I have to be frank. In International Astronautical Congress, there are usually the best scientists in the world working on space missions. But a topic like this one, the one that I'm presenting, my goodness, is regarded as a bit outside the main field, you know. So it was a miracle that they were not rejecting our paper in some sense. Okay. Anyway, I conclude with this. Nicolò and I have been working by Excel, of course. We put all the distances, the radiuses of the stars, we compute the gains, anything. And we finally hope to find what is the best trail of expansion of humanity in the future. I won't say millennia, I would say million years. But this is not much. I mean, the galaxy is, roughly speaking, 8-9 billion years old. So even if it takes a long time, it doesn't really matter. What matters is to convince the agency, and of course I'm thinking of NASA, but also ESA and so on. I proposed this to ESA a long time, around the year 2000, and I gave a similar talk at JPL in the year 1999. So these talks, like the one I'm giving today here, are just made in order to let me speak clearly, please, to let people open their eyes on this physical phenomenon that we did not know about until 30, 40 years ago. And now, at long last, we are discovering. So I won't give you more details. This is what Nicolò and I are working. Let me just come straight to the conclusion. Conclusion. First, human colonization of nearby stars will be achieved only if radio links will be kept across interstellar distances. We cannot forget about our own past. So I am using this to convince people. Of course, there are many supporters of advanced propulsion, and I agree with them, but my personal opinion is that keeping the link is more important than having a good propulsion system. Because if you lose the link, you are lost, period. Second, optimal radio links are provided by the radio bridges, that is, using two stars as a overall system in order to decrease the powers involved with the communication. 3, the gain of a star is proportional to mass and frequency cube. This is the key information point. 4, humans may create, oh my goodness, their own galactic internet. Journalists love this kind of words. Sorry about that. But essentially, if you use galactic internet, they understand immediately what I'm talking about. If I just tell them the equation, they turn the head on the other side. Right? Anyway, the galactic internet is the goal of humanity for the next few million years. But now a question from SETI comes up. All I've been talking about is about humanity. Who knows? Maybe there have been other civilizations in this galaxy, but possibly also in other galaxies, who knows, that have created a galactic or more galactic internets over the past million years. The point is that we, humans, have no access to that because just now we are realizing how to exploit our own star for the goodness of that. As long as we did not reach this goal, we are completely cut out from the rest of the universe. Okay, non-human civilization may have created galactic internet already. Contacting them is the goal of SETI. Forgive me, I've been the chair of the SETI committee of the IAEA for 9 years, so I've been working on this, including, of course, the Fermi paradox and all that. Finally, point. Exploiting the solar gravitational lens, SGL, is the first step now, as Victor Toth will show today in the afternoon. Thank you very much for your attention.
So, since you've talked about the whole part about the search for extraterrestrial intelligence, I've thought that would this situation, assuming that non-human civilizations are currently running a sort of galactic internet already, would not the use of these star gravitational lens one of the things that sort of enforce the Fermi paradox? Because I might have understood it badly, but like by using these lens, you could potentially use much lower energy to communicate across stars and with much less bleed through. So everything would be much more directional.
Well, it is absolutely directional. You are right. Yeah, unfortunately, this is the number one strict requirement. We have to keep the directionality. I agree with you. So we need a number of focal missions, one for each target that we want to explore. But that's physics. We cannot escape that.
My broader point was there's really no way to see information that is being transmitted by a pair of stars that we are not part of.
Well, I give you an idea, all right? It may be criticizable, I don't know. But anyway, my suggestion is, please let NASA or whatever space agency look for antennas at 550 AU in all directions. If you just find one spacecraft, alien of course, then you immediately have the direction of the source, because it must be in straight line.
It must be in
exactly. So this is the way to discover if extraterrestrials are watching us. Thank you.
Thank you.